Okay, so we were discussing this amortized analysis. Okay, amortized analysis, and in this amortized analysis, we have seen that for a sequence of n operations, we are we are taking we are taking some kind of detail. Okay, we are we are taking some kind of detail analysis, and then we are taking the average. Okay, so that is the main viewpoint, and that could be implemented as well by using this potential method. So potential method, that also we have seen how to tackle that situation. Okay, so with the potential method, how to analyze this amortized cost, that also we have seen. So today what we will see is, we will see one example that is called this incrementing binary counter. Okay. So incrementing binary counter, and this incrementing binary counter we will analyze with first this aggregate analysis. Okay, with aggregate analysis we will first analyze it, and let us see how we can analyze this. This is a different flavor other than the stack we have discussed. Okay, so maybe somebody is waiting, maybe I can allow. Okay, so this what we are doing here. Okay, so this is another example of aggregate analysis, as we are as it is told, and it is as usual. This is from the CLRS book. We are taking the help of this CLRS book. Okay, okay, so maybe we can go back to this original one. Okay, so here what is the problem actually incrementing a binary counter? So you have already encountered this binary counter in, say, digital electronics. Okay, so in digital electronics you have got this counter. Okay, so this we are implementing a k-bit binary counter. So whenever we are implementing 3-bit binary counter, then we are having 000, 001, 010, 011, 1. So that is 3. Then 100, 101, 110, and then 111. Okay. So this 3-bit binary counter. So we are generalizing any k-bit binary counter. Okay. So k may be 3, k may be 2, k may be 4, something like that. And that counter that counts upward from 0. Okay. So we are counting 0 and then 1 and then 2, all these things. Okay. So here we will use an arrow, so use an array, this A0 to this, okay, this notation. So 0 to k minus 1 of bits, where this a dot length GTH length equal to this k bits. Okay, so 0 to k minus 1 means k bits we are having. We are with this array we are taking care of the bits which are changing. Okay, so all these bits information we are having with this array. This information we are keeping track, and a binary number x that is stored in the counter has its lowest order bit in a 0, and its highest order bit in a k minus 1. Okay. So that this x equal to this x is, we can write.
Sir, someone is waiting in lobby, sir.
Okay. Okay, so this x, as you know, this how this number, this x is represented. So this is 1 times 2 power 0, and this is 0 times, so I told this is from 5:30 and it is 5:45, and people are still joining. Why this is? Huh? Uh, so no one will be joined after this. So x equal to this, you can say this is 2 power 0, then 2 power 1, and then 0 times 2 power 2. So this is exactly written here. Okay. So any number x that we can represent this I equal to 0 to this k minus 1, and this is ai times this 2 power I. Okay. So this is the representation of this number. Say this is 3. 3 means 1 times 2 power 0 plus 1 times 2 power 1 plus 0 times 2 power 2. Okay, so this is the summation we can write. And initially this x equal to 0. So this is initially this x equals 0. That means in binary we are representing 0, 0, 0. And thus, can you hear me?
Yes, sir. Yes, sir. Yes, sir.
Okay. Actually, current is not there. Okay, it's other device working fine. Okay. Okay, so this is the setting. Okay, and x equals 0, and thus ai in for this x equals 0 case, ai will be equal to 0 for all I equal to 0 to k minus 1. So this is 0th term, this is 1th, this is second. Okay, so this is 0 to k minus 1. So for all these, the bit will be 0. That is told here. To add 1, so now I'll be adding 1 to this. That means we will be incrementing the binary counter. Adding 1 means we are incrementing. Okay. So what program we have written is that, so we are incrementing this a. So initially this I will be equals to 0. That means each of the bits from left to right will be checking. And while I less than a dot length and ai equals to 1, we are flipping ai to 0. Okay. So, and then this I will be incremented to I plus 1. That means we are looking to the second bit and then the third bit and so on. And whenever we are coming out, we'll be one step ahead. And then if I is less than a dot length, okay, so this ai should be making to 1. So let us take one example of this. Maybe this I can take this one. Okay, I can take this one to illustrate the point what is happening in this. So 0, 1, 1, and then we are adding 1 to it. That means we are incrementing 3 to 4. Okay, so we are going from left to right. Okay, so first I am checking this bit. So first I will be checking this bit. So this is ai equal to 1 and I equal to 0. So they definitely this bit. and if this is 1, then it will be flipped to 0. Okay, and then I will be equal to I plus 1. That means we will be looking to this bit. Okay, and then then this bit will be flipped as it is 1. Okay, as it is 1, right? So I equals to 1, and it is still I less than a dot length, definitely. So a dot length is 2 here. So this is this is the case, or okay. So this I less than a dot length and this ai equals to 1. You can think of a dot length as if I'm starting from 1, so it is starting from 0. So a dot length will be 2. That is okay. So ai equals to 0. It will be if it is 1, and then this will be 0 again, right? And then you see whenever I'm going back here, and then this guy I am considering, this guy, okay, 0. So this condition ai equals to 1 will be failing, right? So then I'll be coming out of this loop, and then this ai, to make it 4, then the last bit should be changing to 1. Okay. So that we have done here. So this is the procedure which is written here. Okay, right. So whenever we are incrementing, now you see how this amortized analysis is coming into picture. So we have to what we are having, a sequence of n increment operations. So in the amortized analysis, we have seen that we are observing a sequence of n operations, and this is exactly fitting in this case, sequence of n increment operations. So sequence of n increment operations we are having here. So that's why this is a perfect candidate for this amortized analysis. So n increment operation, right? So this is a perfect candidate for this amortized analysis. Okay, one guy was waiting, maybe no. So now, yes, anybody wanting to say something? Okay, so this is a perfect candidate for this amortized analysis. Now, how we will be analyzing this? Okay, so so you see this case. Whenever we have taken this case, so this 3 to 4. So 3 to 4. You see at this time. So you see how many flips happening: 1 to 0, 1 to 0, 0 to 1. So all bits are flipped. But you take this guy, 0 to 1. So at that time only 1 bits are being flipped, right? So you see, so 4 to 5, 4 to 5, how many bits are getting flipped? Can you tell me how many bits are getting flipped? 4 to 5. Who will be telling? How many bits are getting flipped? Anybody listening?
3, sir.
Sir, one. Yes, sir. Three, sir.
4 to 3. Sorry, 2.
Four to
So
only
one.
one.
4 to 5, sir.
One, sir.
So one.
1, sir. 1.
One, sir. One.
1. So I think many of you are listening. That's good for me. Okay. So 0 to 1, only this bit is flipped. So 0 to 0, 1 to 1, it is remaining same. So you see, for a sequence of n increment operations, if operation by operation we are seeing, then we see that most of the cases, the flip cost. So that means that is the whenever we are changing, whenever we are adding, that means the shift operations going on here. So that shifting in terms of this number of shift operation, that means how many bits are getting flipped, okay, not shift, getting flipped. So that count will be giving the time complexity of this algorithm, right? So because that is consuming the much of the bulk of the cost that is consuming, okay. So, and we are observing that for a sequence of n operation, for a sequence of n operations, very few operations are consuming many more bits getting flipped there, okay. That means very few operations are consuming a bulk amount. So this as we are getting 3 to 4, here once in a while we are getting this kind of scenario. So you see, if you can argue like this, then you are all set to amortized analysis. So for a sequence of n operations, few operations will be expensive. And these we are observing here that here also the same situation happening. Very few are expensive, others are modest. Okay. So now if we analyze by our conventional method, then we are seeing that okay, at the worst case, all the k bits will be flipped. Okay, so at the worst case, so that will be taking, so per operation cost will be taking order of k, and in number of binary increment operations we are having, so we'll have order of nk time necessary, right? But in that case we have assumed that throughout this order of k cost is involved for all increment operations. But whenever we have taken a closer look on this, then we have seen that very few are expensive and most of them are not expensive. So then definitely we have to employ some other technique, that is this amortized analysis can be, if we apply this amortized analysis, then we can have a very tight bound. Okay. So this is right. So as also we have argued that this is right, but this is not tight. Okay. So now we have to have a tight bound, right? So in this case, what we will be doing is so okay, so it is starting from here. So we can tighten our analysis. We can tighten our analysis to yield a worst case cost of order of n. So instead of order of nk, we will have worst case guarantee order of n. So how we can figure out that? So worst case cost of order of n for a sequence of n increment operations. For a sequence of n increment operations, by observing that not all bits flip each time increment is called, that we have already observed. Okay. So this is, you see, this is how this CLRS book to be read, and it is really enjoyable if we understand all these things. So that's why I have taken the document from directly from that CLRS book, and we are trying to comprehend line by line what it is told. And many students feel that CLRS book is not readable. Okay, but once you are getting a feel of CLRS, then no other book will be you will be following. That is for sure, because what over the years of experience I have seen that whenever I try to switch other book, I am not getting that kind of feeling. Okay, that kind of enjoyable feeling, right? So that's why this is a very enjoyable to study this CLRS book if we can understand. Okay. Okay. So that is we have observed that not all bits flip each time increment is called. So now you see this As figure 17.2 shows, in the next slide we have shown one figure. A0, that means the bit which is A0. So this is our A0 bit. Okay. So A0 bit does flip each time increment is called. The next bit up, A1, flips only every other time. A sequence of n increment operations on an initially zero counter causes A1 to flip floor n by 2 times. Okay, floor n by 2 times. So you see, this is whenever we are having this increment operation going on. So you see this 0 to 1, it is flipped. So this bit is 0 bit, 1 to 0 it is flipped, 0 to 1 again it is flipped, 1 to 0. So every time we are calling the increment operation, this bit is 0 is getting flipped. Okay, is getting flipped. So that's why we are seeing, okay, this is this that is what the CLR's book is telling, that this bit is 0. It is getting flipped and it is quite observable here. And this, what about this A1 case? What about this? So bit by bit throughout a sequential operation, what are the possible flips we can have, that we are trying to analyze. Okay. And then if we sum it up, then that will be giving the total cost, because we are measuring the time complexity here in terms of the number of flips of the bits, because that is what exactly happening whenever we are incrementing the binary counter, right? So this E1, so we see this every other time. So 0 0 it is remaining same, then 0 to 1 it is flipping, and then 1 1 it is remaining same, then 1 to 0 it is flipping, so and so on. Okay, so this n by 2 uh, n by 2 floor number of times we are having flipped. So why this floor value is coming? You take any value, say 5, and then if you substitute that, you will see that 2 flips we will have. So then 5 by 2 floor will be giving that, right? So this n by 2 floor number of flips we are having. So now you see this similarly, this bit A2, okay, that flips only every fourth time. That means n by 4 floor time. Okay, so this A2 is flipping times in a sequence of an increment operation. So in general, what we can say, so this is n by 2 power 2. Okay, n by 2 power 2. This is n by 2 power 1. Okay, so that is corresponding this A1, and n by 2 power 0. Okay, so every time, so that is for 0 case. So we can say in general, for I equals to 0 to k minus 1, bit AI, this AI, bit AI flips how many number of times? N by 2 power I. So this many number of times in a sequence of n increment operation on an initially 0 counter. So each bit's being flipped, we can capture with this formula, right? N by 2 power I floor, right? So that is so the total number of flips in a sequence of in operation is thus we can represent by this formula. Okay, so this is n by 2 power I for any ith increment operation, and how many such increment operation we will have? I equal to 0 to k minus 1. Okay, so now you see this is, we can write that this is less than, this is I equals to 0 to k n by 2 power I. Okay, so this is the floor. Okay, so floor x less equal to this x. Okay, so that is definitely true. So that's why we can write. And now you see we will be applying that magic formula, that infinite series. Okay, so that already we have seen in one of the problems. Okay, so we can write that this is say less equal to I equals to 0 to infinity. Okay, n by 2 power I. Okay, so that we can say. So this is I equal to 0 to k. We are adding few more positive terms. So definitely this expression will be less equal to this. And why we have done this? Because we have to apply this infinite series formula. So n is not dependent on I, so n will be taken outside. I equal to 0 to infinity and 1 by 2 power I. Okay. So now we have got this I equals to 0 to infinity, right? And that we can say 1 by 2 whole power I. So we have already seen that I equals to 0 to infinity. If we are having this x power I and mod x less than 1, so in that case we are having this formula known. Okay, so this is mod x is half here, so it is less than 1. So now what we can do, we can apply that formula. What will be that formula? Can you tell me? Already we have seen that.
A upon 1 minus r, where a is 1 by 2 to the power 0
No,
and
no,
r is 1 by 2.
no. This you say directly. I have already told you.
1 upon 1 minus x.
Ah, 1 by 1 minus
Yes,
x.
sir.
Okay. So this is the already standard result, and that I'll be applying here. Okay. So 1 minus half here. So what we are getting n times. So this is half and 1 by half. So that will be 2. So that is 2n, right? So you see we have got 2n here. So the total cost, if we analyze, uh, in a very crude way, that means in a detailed way, right? Then we are getting that the total cost which are involved is 2n. Okay, it could be upper bounded by 2n. So the total cost we have got initially from the zero counter is this order of n. Okay. Then the average cost of each operation will be order of n divided by n. Okay, so then order of 1. Okay. So average cost, that is the amortized cost per operation we are getting is order of 1. Okay, so that is the much tighter bound, and worst case amortized cost is order of n. Okay, this worst case cost we have analyzed, and this amortized cost, as this amortized cost is the, we talk in terms of this average cost per operation, so that will be order of 1, and that we are getting whenever we have got a tight bound on this total cost. Okay, total cost in worst case. So this is how this binary counter we can analyze for aggregate analysis. Okay, so uh, today up to this, and in the next class this aggregate analysis we can for this binary counter we will be also analyzing with this potential method. Okay, in the next class. Potential method, right? So today up to this, and thank you for joining this class.